We present a novel control strategy for autonomous cutting of soft tissues under visibility constraints. The key motivation for this project is the wide local excision, a surgical task of tumor extraction with a clear margin of healthy tissue around it. One of the key challenges of this task is cutting along an uncertain boundary under significant visibility constraints. Human surgeons often rely on tactile cues to guide the excision within the desired region of operation. In this work, we address this challenge for autonomous cutting by applying the probabilistic inference to define the desired region of operation and using the probability as an error signal for closed-loop movement correction. We evaluate our method in the task of scooping a grapefruit with a regular knife. This task presents similar challenges to the surgery, mainly the complex and uncertain geometry of deformable environment and contact reach manipulation between two mediums of varying mechanical properties. Most importantly, this task implies the requirement of keeping the knife on the boundary of two mediums. Since the exact boundary between the peel and the pulp is unknown, it must be inferred during the execution. The key insight comes from observing this task performed by humans. It is clear that humans don't rely on accurate geometrical model of the fruit, but instead use a general scooping motion with occasional corrections applied when necessary. For example, if knife enters the peel where it becomes less maneuverable, the movement is adjusted or completely restarted under a different insertion angle. Our hypothesis is that cutting along the desired but unknown boundary is done by following a rough nominal trajectory that is modulated in response to the probability of entering either of mediums. We hypothesize that such probability can be inferred from sensing the resistive forces that arise from mediums being separated. In other words, we are using the medium classification probability as an error signal for closed-loop movement adaptation. This approach enables to compactly encode the desired operational region in the decision boundary of the medium classifier. We start by learning the nominal scooping trajectory and then use it to train probabilistic classification of force readings associated with operation in either of mediums. Finally, we close the loop with a control scheme that corrects the nominal trajectory according to the classifier's belief over the mediums. We use the dynamic movement primitives to encode the nominal scooping trajectory. The learned movement was evaluated on the scooping task, where the main objective is to successfully extract grapefruit segment without the knife getting stuck in the peel. The prescribed nominal scooping motion showed poor generalization to another grapefruit with different geometry. In most of the failed trials, the knife would enter the peel, with the rare exceptions of knife tearing through the peel and destroying the segment. The multiple successful and failed executions revealed distinct traces of torque measurements generated in the joints of the robot arm. Each of such traces consisted a time series of 24 torque samples. These samples were used for training the classifier to disambiguate the mediums by predicting the knife's deviations from the boundary. We labeled the torque samples from the successful task executions as pulp and torque samples from the failed task executions as peel. Such training process is inherently noisy, since all of the 24 torque samples in the sensor trace share the same label defined by the outcome of the task execution. This means that even if the knife was closely following the desired boundary throughout most of the execution but got stuck in the peel at the very end, all of the 24 torques readings would still be labeled as peel. However, we believe that such training forces a more conservative probabilistic model. One of the main criteria for the medium classifier in our task is to report the appropriate levels of uncertainty without committing to overconfident predictions. We found a linear logistic regression model a suitable candidate with a well-calibrated probability output. Despite misclassifying some intermediate samples, the trained model does not commit to any extreme beliefs over the mediums unless the torque is a strong representative of a given class. Importantly, in the case of ambiguous inputs, the model demonstrates desirable levels of uncertainty, which is extremely important as we use probability as an error signal in the feedback control. In our experiments, we use a simplified motion correction scheme along a single Cartesian axis, in which the first half of the scooping motion is modulated horizontally, and second half of the execution is modulated vertically. In each case, when the probability of the peel increases, the knife would deviate towards the pulp region. The more complex schemes of modulations are possible, for example, the modulation in the direction normal to nominal trajectory on the two-dimensional movement projection. The local correction to the current point on the Cartesian path of nominal trajectory is given by the probability of the knife being in either of mediums. In our formulation, the desired region of operation at each time step lies at the boundary between two mediums, where the ideal classifier would report the highest uncertainty score, the probability of 0.5. For this experiment, we conducted 50 trials of grapefruit scooping on randomly chosen segments in a total of 12 different grapefruits. Our experiments show that proposed movement correction scheme, where the nominal trajectory is modulated in response to the probability of being in a given medium, considerably improves cutting performance. In the future work, we are planning to develop more complex movement adaptation schemes and extend this approach by including higher-level movement planning.